Hello, everyone. Good afternoon. Thank you for having me. My name is Shalini Jagnarine-Azan. I'm based in the Caribbean Regional Group, and I'm the Vice President for the Americas. Today, I'm actually going to speak to you about failures that are often observed after major hurricanes and earthquakes, predominantly in the Caribbean region. It is an interactive talk, so please feel free to interrupt me. I will be asking a couple questions as we go. So I do hope that people unmute themselves and give some responses along the way so we can have a learning experience together. I unfortunately have never been to South Africa, so forgive me if some of these things are not fully applicable. However, structural engineering and physics remains the same globally, so it should be a good experience. Right. So looking at statistics globally, from data compiled by the World Bank, the vast majority of economic damages from natural hazards as a result of floods, earthquakes, and storms, as you can tell by the chart. For South Africa, it remains about the same. So the vast majority, I would say, would be because of storms, followed by earthquakes and floods. Now, this is a short video. I'm only going to show you part of a clip. And this is from Hurricane Maria in 2017 in an island called Dominica. It has a population of about 230,000 people, standalone island. And this is a typical example of what a country looks like after the impact of a major hurricane. You can see that there's widespread catastrophic damage. 98% of all buildings in this country sustained some level of roof damage or complete destruction. I wouldn't show you the entire video, but it's just an example of what it looks like. Pay attention to this river because I'm going to ask about it in a short period. Right. So just to set some context between what you use in South Africa, which is the Beaufort scale, for wind speeds versus what we categorize as hurricanes. So you run from scale 1 to 12, and your maximum being a category 12, which has wind speeds of about 32 meters per second. That's equivalent to about 73 miles per hour. That is a category 1 hurricane. That's not what we call a major hurricane or a major typhoon or cyclone. That starts from category 3, looking at these wind scales. So the video that I just showed you for Dominica, that part of the country experienced category 4 wind speeds, which is about 65% higher than what your category 12 is in the Beaufort. Now, again, an image of Dominica. And I'd like people to unmute because I'm asking a question now. So pay attention to what you're seeing here, and then tell me what's wrong with this photo. Is there anyone who's willing to respond?
There's no damage. Why is there a car standing there? And the roof on the building on the right, other side of the river, is still on. Both roofs are on, and that tiny little shed is still there.
Yes. So this photo was taken probably about 2 months after the passing of the hurricane. So we had already cleared the space. But what I'd like to highlight is in this photo, there's a lot of debris and mud and considerable water damage that came in. And it's because of this river here is the central river that passes on the capitals on the right-hand side, Roseau, and then there's another part of the town, which you saw in the video. During the hurricanes, because of debris that came down and the low elevation of this bridge, plus the bridge that I was standing on when I took this photo, that's the reason why the blockage of the river resulted in water and debris and just widespread devastation because of the volume of water that spilled over on either side. So as engineers, when we're doing designs, these are some of the things that we have to pay attention to. It's not just a design for what has to happen today and what has happened for right now, but what could potentially come. Other types of damage that you would tend to see following major hurricanes would be loss of critical infrastructure, so loss of bridges, loss of telecommunication, loss of schools, loss of livelihoods. These are fishing villages. Now, Dominica is a central mountain, basically, and all of the communities lie along the low coastal areas around the island. You'd have loss of homes, and you could tell by the volume of river sediments that you have in these communities, and it's all because of wash down from the central mountain area that came down into communities. Some other photos that look just like that. Loss of healthcare facilities. This photo was from an island in the Bahamas. This was a Category 3 hurricane in 2015. So the photo on the right is a library. The photo on the left is one of the health centers. And this photo here, again, paying attention to what you see from a typical aerial photograph of damage in any given area after major hurricanes. Tell me, what would be the impact based on this photo that you see? Are there any? This is where I'm waiting for someone to respond again.
I would think impact would be no access, no services like electricity, water, stuff like that. We don't see this in South Africa, so I'm taking a huge guess now.
Yeah.
Sorry.
So actually what it is you see the volume of debris and waste that's produced because of damaged structures and buildings and facilities. That all has to be collected and deposited in an area. Now, Dominica is only 750 square kilometers, or just under 290 square miles. It's a very small space. And you have football fields. This is the standard height of an electrical pole. So it's about 8 to 10 meters tall. And this is just one of the sites where they started collecting and depositing debris. What they had to do was they actually had to reclaim land into the sea to be able to locate all of the waste that's produced following the damage of such an event. Because we have very small islands, it's these types of failures where you have to think about, okay, after we've had damage, what do we do with collection of waste? What do we do with biomedical and hazardous waste? Because the landfills were waterlogged and could not be accessible. And you also can't store or deposit contaminated waste into those areas anymore. What do you do with all of the plastic water bottles that have to be brought in by barge or by boats into these islands to give to the population? I mean, the hundreds of thousands, probably even millions of bottles, plastic bottles, that is just as a result of having to respond to the event after the impact of a major hurricane. So some other considerations that we don't just pay attention to as design structural engineers, for example. Now, to specifically look at some of the failures, the structural failures that you would see in buildings, roofs would be number one. You tend to have widespread loss of roofs or partial or complete damage of roofing structures. In this case, you'd see that in some instances, you'd have roof sheets being torn off with the purlins or the battens below. You'd have damage to the actual timber structure where the rafters would fail, or you could have loss of roof sheets. Now, what causes these things? This is what a lightweight timber structure, a roof structure should look like. You should actually have hurricane straps, which are designed, manufactured, and tested for different wind uplift pressures and forces. And those should be applied based on what your wind uplift is at any given connection. Again, it's what it should look like. Sometimes, and what you'd see a lot, especially in some of the older buildings and the traditional form of construction, is where they embed rafters into part of the ring beam. In some instances, they would run a rebar through part of the center of the ring beam. That already causes or results in a point of weakness in the rafter, where you'd find splitting once the uplift pressures exceed the capacity of the member. Now, another thing, this is an example or just a couple illustrations of how you should connect rafters onto the load-bearing structure below. Just two examples, but there are many different ways that you could do it. Just to note that you aren't damaging or reducing your cross-sectional area of your members of your load-bearing rafters. Now, other types of failure would be roof sheets. Roof sheets tend to be something that's it's still vague for a lot of people, and I'll explain why shortly. These are the high pressure zones around roofs, this light yellow area, which are around the eaves and around the perimeter of each segment of roof. Gables and hip roofs tend to be quite common. Hip roofs have a better resilience because of its geometry rather than gables. But the type of roofing screws that you use, the spacing of your roofing screws, the thickness of your roof sheets, how the screws are connected, those are all very important to ensure that you can get adequate resilience. Now, why are roof sheets such a nebulous sort of topic for so many people? It's because, and I don't know what they use in South Africa, you could probably tell me, but how do you specify when you're saying that you're going to use a galvanized roof sheet over a building, what do you specify it as?
Do you mean how do we specify the thickness or the spacing?
Yes, the thickness.
So typically in South Africa, you would have roofing contractors that specializes in that type of design and details. So they would tell you where your rafters or your truss spacing would be. Sheet thickness really comes from the sheeting specialist suppliers again. So it varies from thickness 0.5 to 0.8, and sometimes over more thick. So it's all dependent on the type of sheeting that you want to put on. And then obviously, yeah, there's a lot of things that goes with the type of sheeting that you use.
Okay, that's great. So you specify in terms of millimeter thickness, 0.5
Yes.
to 0.8. Yeah,
that
on
is.
this side of the world, and perhaps that comes from the US and the United States, I'm not sure, but we specify as gauges. So when you go to purchase a roof sheet from a supplier, they would say, okay, we have 24 gauge roof sheets, or we have 22 gauge roof sheets. But gauges are not standardized in the industry. So one supplier, a 22 gauge might be 0.5. For another supplier, it might be 0.65. And the thickness of the roof sheets, this type of failure is very common as well, where you'd have sharing of the sheets where the connectors are made. And so the sheets get ripped off. This was just a simple check I did for the exact same span, the exact same supports, the exact same roofing screws onto the sheet. And the difference between a 0.45 millimeter thick and a 0.55 millimeter thick is the 0.45 is 26% weaker. That means that the likelihood of that being shared off because of the wind pressures that you now have is higher than a 0.55, but you and your neighbor both went and purchased 22 gauge roofing sheets. And people don't understand why some are failing and some are not. Some examples of roof sheets that actually stood up. This was from an island called Petit Martinique, which is off of Grenada. This experienced Cat 4. It was a Category 4 Hurricane Beryl. This was the largest. This was the first time we ever had a Category 4 hurricane so early in the Atlantic hurricane period. So it occurred between the 1st and 2nd of July 2024. Of wind speeds of 150 miles per hour or 67 meters per second. And this is a roof that's right on the waterfront, not this building actually. It's right on the waterfront, which stood up beautifully. You can tell that it wasn't a new building. Some of the roofing screws were partially corroded. I hope you can see the spacing of the roofing screws, but it just goes to show that if it's done well, it could stand up. Now, this photo here, could you tell me what's wrong with what you're seeing? Anyone? If I could see names, I would randomly call someone, but I can't see anyone.
The committee has said it's warped timber.
Exactly. So this photo, I actually took this was again in Dominica when we were in the rebuilding phase. So after major events, you would always hear international communities come back in and speaking, build back better. This was the sample of the timber that came in from different parts of the world for reconstruction efforts in Dominica after the event. And you can see their warped members, you can see their splits. If you looked along the length of the member, you'd see some members that have a lot of knots. We're not sure about the treatment of the timber as well. So But all of these things, if it's not checked properly and it's not assessed properly, and when you're in a country where you lost everything and you're now dependent on receiving supplies from international donations and from UN agencies and NGOs that are coming in, and these are the materials that you get, this is what's distributed across the island to start reconstruction again. So there's a document that we did as part of the Pan American Health Organization, PAHO WHO, on hurricane-resistant buildings. And some of the checks would be to ensure that you are using suitable materials. So these types of materials, you could probably only use about 40% of the lumber that you see here, and some were not usable or should not have been used. The geometry of roofs are very important. Usually for lightweight timber roofs, the ideal geometry should be a 30% pitch or a 7 and 12 rise to run. That's very steep, but when you have steeper pitches, you have a reduction in the wind pressures that roof experiences. The other thing that you can do is you can build parapet walls around the perimeter of the roofs. That also reduces the wind pressures that you'd normally get in your high wind zones. And this is just a typical example of how it could be done, because a lot of times when you have these, waterproofing tends to become a problem. So you tend to get leaks at these areas, or you tend to get a large volume of water that comes in that can't be taken off quickly. Because the other thing that comes with storms and hurricanes and different events would be sometimes not high winds, but a lot of rain. And so all of these things, it's a multi-hazard event, and our countries are multi-hazard zones. So we'll speak a bit more about earthquakes later on, but there are so many factors that need to be considered when we are doing designs as engineers in this region. Some examples of buildings with ideal geometries that stood up. These are, we call them chattel houses in Barbados, but these were in Dominica. Again, category 4 hurricanes. You can tell from the damage of neighboring buildings, but these stood up beautifully, no damage whatsoever, completely functional after event, not even the loss of roof sheets, even though they've been there for a while. Other types of roofs that perform remarkably well in these events, in both hurricanes and earthquakes, would be folded plates or shell roofs. So this is a pyramid type folded plate with stack ventilation, which is great for the increase in temperatures that we're experiencing as well because of climate change. Some other examples of folded plates would be these two. These were from schools. Now, the waterproofing, especially on the facility on the left, probably had never been reapplied since the building was first constructed about 30 years ago. It still doesn't leak. The roof, the reinforced concrete section of the roof is actually only about 2 to 3 inches, so 50 to 75 millimeters thick, with a thin layer of mesh reinforcement for anti-crack. And fantastic structures. The lightweight also attracts lower seismic loads, which makes it ideal for that type of multi-hazard region. Another type, this is just a simple cylindrical shell roof as well. This was done over the central medical stores at the hospital, where we lost all of the medical supplies to the country after the event, because this roof sheet was put on temporarily right after the hurricane so that they could find a space to put back in materials, but we eventually demolished that and built this instead. Now, the next weakest link after your roof. So you could tell from this photo that the roof structure is completely gone. In this case, there obviously wasn't adequate connection between the actual lightweight timber roof onto the supporting walls below. But let's say the roof stayed on. What would be the next weakest point in the structure? Can anyone tell me from the photos that they're seeing?
Yeah, those lintels or beams across the veranda opening are not deep enough. It would have bent that upwards. It would have pulled that apart at the edges.
That is a possible. Sorry, that is a possibility. The other possibility is you could have the failure of the parapet walls first. So when I visited these facilities, what I noticed, and what's not so visible on the exterior of this photo, is this continuous crack that went along between the top of the lintels and the parapet walls. So it's likely, now I didn't do invasive investigations because that wasn't my requirement in this case, but it's likely that the parapet walls are not adequately or securely connected to the ring beams. And in that case, you can have these things happening. I mean, when you don't have sufficient reinforcement. Both of these structures were destroyed because of hurricane winds, where you have unreinforced masonry or poorly reinforced masonry structures. Some examples of how it should be done. I mean, this doesn't show the horizontal reinforcements and stuff, but really you should have what's the term I'm looking for? Where you confine the masonry on the inside of parapet wall. So you're effectively creating beams around the entire perimeter of the element. And then you reinforce that. And of course, you have vertical reinforcement that ties back into your load-bearing walls below. These are just some other examples of, I'm sure you all know how to do reinforcement for block masonry, if block masonry are used commonly in South Africa or not. This here is to show about windows, and we'll speak a bit more about windows shortly. But the gentleman who just spoke to me was speaking about lintel beams. And this was from another facility at the hospital, a psychiatric building actually, at the hospital in Dominica, where this would have been, and sorry for speaking in feet and not meters, well, it's about 60 feet or so, probably 80. And the entire lintel beam off the eave of the roof was ripped off and slammed onto the lightweight timber roof on the inside, on the interior space of this building. There were patients in the facility at the point in time when this occurred. And that happened because of the inappropriate connection between the reinforced concrete column and the lintel beams. Any questions on anything that we've seen so far? Okay, not yet. All right, so we'll move on to other aspects of the building envelope, which are also very weak elements of buildings as well. So even if your roof stays on, once you lose or there's penetration through any part of the envelope of the building, because of the very high pressures of winds, the rains that move almost horizontally, the damage and destruction that you get on the inside and the loss of your furniture, your equipment, your stocks and supplies, well, it's catastrophic. So windows are the next aspect that we'll speak of. There's also lack of planned preventive maintenance. So oftentimes when structures start looking like this because of lack of termite treatment or regular treatment and water damage over time, it's easy to lose structures. Now, windows, these are just some examples. In some areas, and what architects tend to love to do in our region is to create these aspects of stack ventilation, where they put these fixed louvers just on the underside of the roof slab, so you can get the hot air leaving the space. One of the things that we're advocating for is that architects ensure that we either include hurricane shutters that go over these that can be closed, or there's access so that you can put on timber. Once you have a minimum of 3/4 inch plyboard that you put over these elements, that can stop flying debris. Other than that, if it's less, it can pierce straight through and then go straight into your facility after that. The photo in the center was taken from the Philippines after Typhoon Haiyan. That was a super typhoon. So the wind speeds of that event was about 312 kilometers per hour on the eye wall of that storm, which is over 400 miles per hour. That's why they categorize it as a super typhoon. But glass louvered windows, which are still prevalent and still existing at many of the older facilities that we have in the Caribbean, those break easily. They're vulnerable in hurricanes and earthquakes. So they shatter, they can cause injury to people. This is just an example of how not to do windows because of the lack of overhang on it. You can tend to get a lot of water that comes in around the window frames when you have these events or in regular rainfall periods. What we do advocate for is NOA, so it's Notice of Acceptance to Miami-Dade County. So these types of windows, so they do shutters, doors, exterior doors, and windows, and they're tested to meet the specifications, for instance, that we get here in the Caribbean, because Miami, Florida is just, you know, a branch off of, from where I am in Jamaica, it's less than an hour flight away, and they also get hurricanes. You would have seen Hurricane Helen that impacted the western side of Florida, as well as other states in the US. What they do is you test for high winds, you test for small missiles, which are small debris that comes in hurricanes, large missiles, and you test for driving rain. Once it's tested in the lab and that batch is approved, you install it in accordance with specifications and you can get the resistance. Usually though, and this is where one of the problems starts, a lot of them are only tested and rated for category 3 hurricanes. Now, category 3 was fine probably 10 years ago, where you'd only get maybe one major hurricane beyond that, a Cat 4 or Cat 5. Now, because of climate change, we're going to start having more category 4s and 5s because for this season, we've already had 2 category 4 hurricanes that devastated the countries and areas that they impacted. My little dots here would show samples of how screws should be connected into the actual structure. What you'd find sometimes is people put lintel beams over windows, but around the sides, especially if it's block masonry, it's not reinforced. If you are using NOA rated, and it depends on the type of element. So accordion shutters like these would be anchored top and bottom only, but windows, for instance, have to be anchored around all sides. You can't just anchor it into a hollow concrete block because then the next point of failure would be that connection between the block and the window. There's nothing holding it, so that would fail, and then eventually the window would probably get blown out. So that's why the 3D image that I showed a while back where we indicated reinforcement around windows and doors. Now, storm surge is a major event. These photos were from the Philippines again in Tacloban following Typhoon Haiyan. That was very devastating because of the magnitude of the storm surge that came with it. In some areas, like in this area where this wall was taken, the storm surge level was about 13 feet high. So that's about 4 meters. Approximately 6,000 people died. Now, usually in a hurricane where you just have high winds and not a massive storm surge, you could have tens of people, dozens of people going missing or fatalities after the event. Once you bring water into that equation, your fatalities increase exponentially. So here, between 6,000 and 10,000 people died because of these. These photos were taken around hospitals. This was a village on the coastal community where ships came in and just washed and destroyed people's homes, and they had nowhere else to go. So it's massive. And bearing in mind that, I mean, this is well inland, let's say. This is not right on the coast, but that's a type of damage that you can get from walls that would be normally safe and suitable had it not been for the storm surge. This was from Hurricane Helen. So that's the other category 4 that went and hit the west coast of Florida. One possible solution, so this is one of the communities where that storm surge went into the bay and washed in, where all of the structures around it, probably except this one and this one, stood up because they have these massive elevated columns. These solutions can work well in Florida, but they can't work in the Caribbean because we also have earthquakes. So these would be categorized as soft stories likely. I mean, this is probably a timber structure at the top, so it's also lightweight. So once the columns can withstand that lateral load, it should be okay. But if we were designing, say, for the multi-hazard zones that we're in, you'd have to have more careful consideration. Now, earthquakes. So moving on very quickly. This is a photo of a hospital, Hospital La Cille, which was closest to the epicenter of the 2021 earthquake in Haiti. So not the 2010 one. I did not go to that one. I was too young. But 3,000 people died in this earthquake. It was a 7.0 magnitude. It occurred in the south of the country, where it's not as populated. So the 2010 earthquake occurred in Haiti, which is the capital. Hence, hundreds of thousands of people died. In this case, thankfully, it was not as populated, but you do have this type of damage that occurs. So why does this happen? Well, other types of damage that are quite common would be shear cracks in walls because of lack of reinforcement or because of ad hoc additions. So you would, what you'd find happening here a lot is you would get an architectural design, a layout, and then you would do a structural design based on that. And the structural design may just be the beams and columns and the structural frame itself without any consideration to the infill masonry walls or the partitions or whatever goes into that space. And once you put stiff elements into a building, it will attract load. So if these weren't designed as shear walls, then they will shear because lateral loads will get transferred to them because of their stiffness. So how can we treat with these elements? So a lot of these were refurbishments that we had to do. Out of these two photos, I have photo A and photo B with illustrations. What would you say would be the better solution for that type of shear crack that I just showed?
Reinforcing in the joints.
Yeah. So this solution on the right-hand side would have been for cracks that are not as critical. And then what what they recommended here, actually, they did put rebar on both sides as well. So what they did here was they took away some of the mortar. They put expanded mesh on both sides. So then you can prevent the transfer of that crack. You can add back a bit of tensile strength to the wall in that area. In a lot of instances, in order to tie the segments together and ensure that you get the transfer of that shear, you would have to cut recesses into the wall and put your horizontal bars back in addition to the anti-crack mesh that goes on both sides of the walls before you can tie them back in. And these should be tied on, hopefully, to horizontal bars that exist within the wall. If there are no horizontal bars, then of course we have bigger problems. There's another solution where I've seen some people actually build out a frame. So they actually build out a cage, a steel cage, horizontal and vertical bars, and they build the wall out. If that is an option, that could also be done. It's expensive. Sometimes you may have to just demolish that section of the wall and then rebuild it suitably. Now, do people have a good understanding of piers and spandrels in masonry walls? Are masonry walls common in South Africa?
Yes, they are.
It's not?
Very common. Very common.
Oh, it's
yes.
very common. Right. So
Yeah.
then you should have a pretty good understanding of piers and spandrels, where spandrels are the ones that span over openings like doors and windows especially, and it effectively acts like a beam to transfer load between the piers, which carries our gravity load down to foundation or down to lower load-bearing structures. They're effectively slender beams and columns, so that's how it's framed up. Based on your knowledge of that, what would you say would be the cause of failure of this hospital L'Asile in Haiti?
Short column. The shear failure and short column failure.
Yeah. So absolutely.
The wall.
Yeah. So it's likely that hair failed first because maybe it was an ad hoc piece of work, or maybe it was part of the architectural design. But these sections of the piers, because there is a beam here that stood up well, good resistance, no failure at that point, but it's shared at the next point. So yes, this effectively created short columns into our piers, and it's shared across those sections, and then that likely transferred over to these cylindrical columns that also shared because it was just overloaded. And then pancaking of the building. Now, where do we start with? And this is always, this is often a question where people come and they say, well, what do we need to do? We have so many hazards, we have so many problems, where do we start? And I always say, you start with a fundamentally stable geometry. Excuse me. Out of these images that you see here, which would you say would be the most stable geometry on this file? Or which sections would you consider as stable or regular versus irregular?
Group of one are quite regular, especially the square. Two, you're getting all sorts of eccentricities and asymmetries. And three, obviously breaking it up, you're sort of taking those shapes of two back to one, so they're more predictable, they're more symmetrical.
Exactly. That's absolutely correct. So these are regular structures. They tend to be a lot more stable. These ones, because you have let's call them re-entrance sections. So you have sections that are too long, so you can have torsional distortion across the length of the structure. You would tend to have concentration of higher stresses at these points, wherever you have changes in the direction of the geometry, and then you can have a lot of failure or sharing across these areas. So once we start introducing separation joints into our structure, you can make irregular plan structures into regular shapes. What makes these buildings irregular? Because it's false regularity. You stand on the outside of the building, you look at it, it looks like a square or cube, and you're just like, yeah, that's great. That's a safe building. I would say it's all right. What about these buildings make them irregular?
You got two stiff sides and two less stiff, more flexible sides.
Exactly. Yeah, you guys are great. Come work in the Caribbean. So yes, so we have this could often be a stairwell or lift shaft. If it's not designed, because your center of rigidity now is now going to be concentrated closer to your stiff elements. So it moves away from your center of gravity. Your center of gravity may be somewhere here. Your center of rigidity now may be somewhere here. And because of that, you're going to have torsion around that point. Same thing happens with you introducing block walls to some sides and then probably putting in a glass facade on the front. So working hand in hand with architects, ensuring that they understand these concepts and they work with you. So, you know, to make this one more regular, what would you do? What would be your suggestion?
You could try and introduce panels on the corner.
So
Stiffen up
here,
that corner.
yeah, we could do that. We could also shift. So say, for instance, this was a stairwell and a lift and a stairwell. You could shift the locations. So you could probably put one on two diagonal ends. So then that starts bringing in, because you'd have to do checks for your center of rigidity. So you start designing it so that you try to get your center of rigidity as close as possible to your center of gravity to reduce that. The other thing about doing designs like these, which you wouldn't often see anymore since 9/11, is because having just one central access and egress across buildings aren't acceptable anymore. You need to have two means of egress. So you could split this up now and then put them probably on two far sides of the building. And that helps to bring back not just the lateral stability, but it also helps with your emergency egress. Okay, now on to elevation irregularities. I think this is pretty simple for you guys, where in this case, and you'd probably see a lot of commercial buildings that look like these, where they try to create this impressive opening and facade and entrance into the building, where you have much taller columns that go into a space. Because of that, you will have, they effectively behave like soft stories, because these would be a lot more ductile than the other columns that are broken by the floor slabs, the diaphragms that break them up. So you can have failure across this line. In this case, maybe they created a parking lot on the base. So because my walls, my rigid walls don't continue all the way to foundation, this now becomes soft story columns. In this case, you just have a change in elevation of one or two of the floors. So because it's a lot longer and it's now changed, the behavior of these longer, taller columns or slender columns behave differently to these ones. So they have to be checked, and you have to ensure that it can carry the lateral load safely. A lot of times we would have here as well, because of building on hillsides, where you have taller columns probably on the front or the back of the structure, and then short columns in some areas. Again, these columns would behave differently to these ones, and you could have these columns sharing across this point. So they need to be checked. So again, soft story failure. This photo was taken, there was I call it a baby earthquake, right? Because it was a baby earthquake. It was not a major earthquake here in Kingston last year. Quite a shakeup. I mean, we had broken pipes and electricity went down for a while and tons of traffic because all the traffic lights went down and stuff. But this is just an apartment complex where they tend to do a lot of basement parking in the area. And then they create these ventilation between the retaining wall on the side of the parking lot. So it's a cheap way. I mean, natural ventilation. And so because they've done that, they've created short columns into the space. Thankfully, again, it was not a major earthquake, so you didn't have catastrophic collapse, but that's what could happen because of this type of design. That's very common to see, especially here in Kingston, Jamaica, where I live. What can we do? This was an elderly inpatient facility in St. Lucia where we were doing retrofits for resilience. So again, because of this natural slope of the land, they created a space for their laundry under the kitchen and the facilities at the back of the hospital. And it's vulnerable because you have a soft story area. So we just put in some shear walls, we changed out to NOA rated. Well, we installed NOA rated shutters. All of these doors would be hurricane rated as well. Never mind you see louvers, but they're actually louvers on the fixed inside of a mesh section and glass. So the drive-in rain wouldn't be a problem. But these are some of the work that we have to do in some of the areas. This was also in St. Lucia, because we couldn't get things like that, and because of the use of the space, we had to introduce jack into the columns, introduce a lot of new columns along the length of the walls to ensure that we got suitable lateral resistance. In this case, we had to do some straps to the timber rafters in some areas to ensure we had adequate uplift resistance, and just general sort of upgrade to the age, the deterioration cracks to the building. So again, typical types of cracks that you'd see that cross pattern cracks between window openings because of the change in direction of lateral loads that comes in. You'd see a lot of re-entrant cracks, and these are very common. Some of the ways that you can deal with that is, yes, you have to have that beam now that comes around lintel sections. In some instances where you have this architectural design where beam windows and doors don't line up, and sometimes you can have them staggering and going up the height of a wall. Those have to be checked carefully because now your piers and your spandrels change and you need to now transfer loads, so not applicable everywhere. In this case, to add some lateral resistance across the length of the building, and also to ensure that your parapet walls stay on and then your rafters that are there. So they did strap in here, this illustration is with timber cross bracing, but you can also use steel cables that can do it as well. So just some illustrations of how we can treat with, small, simple buildings. This is from an illustrated guide for the OECS, the Organization of Eastern Caribbean States, where Dominica, St. Lucia, St. Vincent, all of those countries are part of it. And it's a great little document because now builders and laymen can look at it and say, this is what I need my building to look like. So it's quite well done. Now, coming to the end, again, because of climate change, and I saw that South Africa, the highest wind speeds that you tend to experience is about 44 meters per second. That's about, 69 miles per hour, somewhere thereabouts. Because of climate change, and you have a lot of towns along your coast and stuff, you will also experience increasing wind speeds and higher intensity storms. And then, of course, more erratic rainfall. Well, you also have floods, but I didn't touch on floods really in this presentation. But these are things that you need to be aware of and that you need to consider. And perhaps, I don't know if there are checks and if they update their hazard maps regularly, because it's something that we're looking at doing now in the Caribbean again. The last time we updated it was in 2018. But it needs to be checked and updated regularly, because what you may find is that you now have higher wind speeds than you had 10 years ago. In the Caribbean, we also include a climate change factor. So for categories 2 buildings, we have a 15% increase in wind speeds because of climate change. And we have a 10% increase in wind speeds for categories 3 and 4, the importance categories of buildings. So that helps to not just use the wind speeds that you see in your codes, but to actually account for the changes that will come. Now, what are your takeaway points from this presentation? And this is where I open it up to the 41 people who are listening. I want to hear from all of you, please. See, we have a lot of people offering.
Lesson learned, I think, from our group is that the devil is in the detail. It's very important to get your details correct.
And do it right first
The
time.
first time, yes.
Is that Ron I hear?
Yes, Ron.
Oh, Ron, nice to hear you. I hope to see you soon. I hope to see you soon. Well, lovely to hear. Absolutely. Get the details right. What else? Did anybody else take away anything else from the presentation?
To the extent, get the concept right.
Yeah, absolutely. Yeah, that's where I usually start. You get your structural, conceptual design done correctly, to withstand all of the hazards that you have based on your site location, and you're 85% of the way there. Anything else?
I think for me, what strikes me is that the fact that people don't understand what structural engineers do, and people just ignore, they just do things without taking into consideration what we do, and that's a big issue in developing countries or in very poor countries where people just do things and the authorities don't clamp down on these things. So that's my take on this, because the same problem like I'm seeing there is I do have that also in my country as well. So
I agree.
it's quite a-
I agree.
Yeah,
That's a big point. Mhm.
also on a similar thing, I think the codes are normally good, but it's the application of codes that are often wrong. I know, like with the Haiti one, my wife was there in 2010, just after that earthquake, and it was, you know, the pictures were crazy. The extent of damage was there quite a lot. Did you notice when you went there 2021 that they had improved the building standards? Were the new buildings built better, or I've been cheeked to the answer. I think a lot of it's implementation of codes that are the problems.
Yeah, so I've been to Haiti quite a few times actually, because I'm going there on Saturday again, to look at some hospitals in the north in Cap Haitian, which is also on a fault line, a different fault to the one that destroyed Port-au-Prince. There are a lot of the GDP of Haiti is very low. Haiti is the poorest country in the Western Hemisphere. And the security situation, I'm sure you may have heard of it because of police officers from Kenya who are there now. But the situation is very dire. It's not like any other country that I've ever been to in the world before. And you'd find that there are a lot of very, very poor people. And they build in these, you would have a slab that somebody started off with, and they built a little room, and then somebody else would come and they would build on part of that room, and they would go up, and then somebody else would come and build another section, and then they would extend it. And so that's a lot of the type of construction that you would see. There's a place called Jalousie in Port-au-Prince, which is like the favelas in Brazil, where a lot of people just build on the hillside. They would displace populations from the earthquake, and they just relocated and built these temporary, permanent places to live. There's no adequate running water or sanitation in those areas. But access to schools and hospitals is also a big problem. So I wouldn't say that it's changed considerably. There's still a lot of work to be done. But yeah, your wife would probably go and say nothing much has changed, unfortunately. Sorry, Steve.
Thank you very much for the presentation. Just a quick question. You mentioned the guide that you guys are distributing to the more, let's call it informal builders, that they can learn from the guide how to construct. Is there a chance that you can share that guide with us?
Oh, absolutely. Yeah, because I think it's also on the internet. I mean, I know some of the authors. I will share the guide and I can share the codes. I don't see why that would be a problem at all. And it's a lovely little document. I mean, there's some great images. A lot of the 3D renders that I used from it came from that guide. So I thought it was very nicely done. And so, yes, I will share it. I'll send it to Marlies and ask her to circulate it.
Because our climate is changing, and every now and then we get a tremor up here in an area that it's very light. It's nothing compared to what you guys are experiencing. I'm very, very glad that I'm an engineer in South Africa. But we are moving into that area that precautionary measures is going to become a must.
Yes.
So
Yeah.
yes. Thank you.
I still Definitely. You're welcome. I still think that one of my major concerns at the moment, I'm having discussions with a lot of my colleagues here, because I've been doing this for the last 13 to 15 years. And when you see firsthand, when you get a firsthand experience of the things that fail and the impact that it has on people's lives, but not just that, the long-term impact. So Dominica, for example, that impact from Hurricane Maria set back the development of that country by 10 years. This little one, and I say it was little, it was a big event, but it didn't impact the capitals of the countries that it passed. So the actual impact on the country wasn't as much, but it would still set back development by about 2 to 5 years, let's say, because we are not wealthy countries to begin with. I mean, South Africa is a fairly wealthy one, which is why that chart that I showed you from those events, I mean, it's less than 1 to 2% of your GDP whenever you have major events like that. But you are going to have increasing temperatures that's affecting everybody around the world. So the question about how is your electrical infrastructure coping with increasing temperatures is one question. The changes in rainfall patterns. So where you may have high intensity rains that were never expected before. So recently in Florida, I was in Florida a couple of weeks ago and chatted with one of my friends, and she bought this home in Florida's a pretty low area to begin with, right? But she bought this home, she'd been there for 5 years, and they were looking at insurances. And FEMA, the Federal Emergency Management Agency for the United States, just rezoned and changed her area together with probably 60% of where people live in Florida to flood hazard zones or flood prone zones, which now affects insurances. So there are loads of impacts that are coming and loads of things that are changing because of climate change. And I think us as structural engineers, we need to be very aware of what that impact could mean on not just the work that we do for people, but on our communities and our own selves. There had some discussions where the head of Price Meyer out of the UK, he had an interview a couple of weeks ago where he said, following events like the earthquake in Turkey and other major storms and hazards and hurricanes and cyclones that you have in different parts of the world, you're finding that insurance premiums are going up. So these are insurance premiums that you pay to governments or large organizations or the ones that are mandated by governments. If you find that insurance premiums are going up because the damage that you have after these events are becoming greater and greater in scale, what he said is that you could find that in 10 years, unless something is done, that insurances would no longer be tenable. If you sustain the kind of damage that I just showed you there, and you as a private person don't have the insurance to be able to rebuild, what situation would you be in? So there's a lot more that we need to be doing globally, and it needs to be a collaborative effort. So yes, I see a question in the chat. I go on and on, I'm sorry. Stop me, right, Marlies? Suzanne has to go. Thank you, Suzanne. I'll hand over to Marlies now if nobody else has any questions or comments.
I think, thank you for your talk. It's been very informative and obviously shows us what we don't see in our country, which we are grateful for. And thank you for sharing your knowledge. It's opened many things in my mind to take forward and implement.